Do you hear me online? It's okay? Wonderful. Gilberto. Un descanso, un coffee break. Would you agree for a 10 minutes of coffee break in between the two parts of the classes? Okay? Wonderful. Can you please invite me to the coffee? Anyway, can I start? It's okay?
Okay, good afternoon to everybody. It's a pleasure to me to introduce Professor Rogelio Palomo from Seville University. He's going to talk for us. It's a short course about the effects of radiation in electronic devices. The course will be in 3 days, and the first day today he will make an introduction, and then Wednesday will be more effective.
Well, we will go deeper.
And Friday, the things
Friday, right at the bottom.
Technologies.
Okay.
Well, thank you very much. Please.
Okay, thank you for being here. To the people in the YouTube, an honor to be invited by the University of Sao Paulo, coming from Sevilla, from a long collaboration we have in between our institution, between Sevilla and USP. So I will introduce today in a 2 hours course with a coffee break of 10 minutes of coffee break in the middle about the radiation effects on microelectronics from the very beginning, starting at a very basic level, and then we will go deeper and deeper and deeper. The technologies I will present today are not the last technologies, okay? That were the technologies more or less standard in the 20s, more or less. Take into account that in electronics, 2 years is an era. So basically, the electronics you have in your computer, on your laptops, or even in your cell phones, is not exactly this one. But anyway, for this particular application, we typically use 10 years old electronics. So it's not too old for our purposes. Okay, which are the environments where we want to put electronics? We want to put electronics in radiation environments. For example, in the experiment I also work with, compact muon solenoid, etc., associated to the program of the Large Hadron Collider at CERN, Geneva and France. So here the problem is about to put detectors and detector microelectronics under basically one nuclear explosion every 25 nanoseconds. Because you have to imagine the LHC not like in the cartoons, like one big splash of particles, but as a continuous flash. So the main problem, in particular with the compact muon solenoid, I remember a seminar given to us by Guido Tonelli, one of the founder fathers of CMS, when they proposed first the CMS. The explanation was you will build a stone detector because it was impossible to have electronics in that epoch, I'm speaking about the 90s, to withstand with the levels of radiation expected at CMS. This is a trigger reactor, very similar to the reactor you have here at IPEN, okay? And the bad news here is the level of radiation, neutron radiation and gamma radiation here is so high that basically we have no electronics, okay? To take measurements in the core, we need to use old-fashioned, old-style ionization chambers filled with gas. So we are starting to control electronics in this kind of environment, not yet here. Where is the origin of radiation outside of the technological environment? Well, basically the take-home message is that space is extremely radioactive. Okay? Radioactivity was discovered 150 years ago in rocks, but when you put yourself into a balloon, then you detect that radioactivity is not decreasing with high altitude, but increasing. The effect is coming basically from the sun and basically from the rest of the galaxy. Now we are starting to understand the origin of cosmic rays coming from the center of the galaxy, coming from extremely energetic environment like the black hole we have in the center of our galaxy. We are protected. Okay, this is the depth of different kinds of ionizing particles coming from the sun. Mostly the galactic cosmic rays reach the troposphere, where you have an electromagnetic, first an hadron cascade, and then an electromagnetic shower, and it's fun to look at because it's aurora borealis or aurora australis. Okay, but it's not good for your health. It's better to stay kilometers away from that. We are protected in our local environment because Earth has our planet has a dipole magnetic field, basically a dipole magnetic field that is deflecting the solar wind, not the solar wind, but the plasma and the coronal ejections and basically protons coming from the sun. But we have technology not at Earth, but over the Earth. So basically the problem with radiation and microelectronics started to appear with the space age, 80 years ago. Space age is very old space age. The first event in space was with the Telstar satellite, the first television broadcasting satellite in 1964, if I'm not wrong, because the Soviets and the people from the US Army, were detonating nuclear bombs in the stratosphere. Going back to relative recent times, the first we lose that the Eres #1 in July 1991. It was a satellite for looking for resources from the orbit. Okay, basically we had 5 days of operation with a lot of anomalies, including soft error and reboot processor. Remember, that was technology from the 90s, so the transistors were extremely high, extremely big compared with the transistor we have nowadays. Okay, so in principle, it was totally unexpected. The problem was, in particular, in the X-band transceiver. This is a very old, in our standards, okay? Very old X-band transceiver, because the X-band transceiver was responsible of the radar antenna. So basically, because the failure was reproduced using protons, and confirmed that the failure was a latch-up in one of the static DRAMs. Okay, a latch-up is when you basically a latch-up is when you make a short circuit due to the impact of a particle. In that case, that short circuit will increase a lot the amount of current going through the transistor affected by the impact, and probably it will burn out. Okay, in that case, it was totally burned out. Okay, satellites are important, but are not critical for our everyday life. Back to the future, 2008. It was a flight, the flight number 72 from Qantas, with a modern airplane, exactly the same airplane where I flew, coming from Sevilla. Okay, was a routine flight, but going at cruise altitude, but suddenly it got 2 consecutive altitude sudden drops with almost 1 negative G. This is the impact of a flight attendant against the sailing in the cabin. Okay, the flight was not destroyed. The Mayday was successful at the end, so they could recover the airplane. And the problem was related with the inertial measurement unit, exactly the same problem with a RAM memory of the processor. So they were in cruise flight, and because of the impacts of neutrons, that particular day, the amount of the density of neutrons was high due to a maximum cosmic rays on top of Sydney. Okay, so basically the computer was interrupted by the single event upsets, and because the computer was managing by flying the airplane, they were almost with a crash landing. Okay, at the end it was recovered. So the problem is important, was important in more than 50 years ago. Today it's even more important. Okay, so it's a problem related not to detectors, but related to everyday life. This is the dosimetry when you fly as a crew in a flight from Sevilla or from Madrid to Sao Paulo. This is the dose you are getting in your body. Okay? For you, it's not critical because you don't fly every week. But for the crew, it's critical because they have to fly at most 4 times. The reason is to avoid an excessive amount of radiation in their bodies, and they are considered exactly like nuclear workers. And they are flight attendants, they're the pilots, etc. In particular, one of the companies in Spain, Iberia, is serving the route from Madrid to Sao Paulo. They were 20 years ago, starting to understand the problem related to total ionization dose, not to single event upsets, okay, not that localized impacts in a moment, but the accumulated dose due to the radiation in the stratosphere at beyond 10 kilometers of altitude. We use different instrumentation. In particular, every long flight from Iberia has a spectrometer Liulin in the galley. Okay, it's now compulsory. Also, the companies that cross over the Arctic, the Norwegian and Swedish airlines, also have exactly the same equipment. This is old equipment. This is an equipment typical in 2004, but at the moment it's not very different what they have to have in the galley, and also in that boxes that serve you the food, okay, to know the amount of radiation in the food. Okay, so we have a problem. This is one of the very last particle detectors. This is the Alpine version #1 chip, and you can see the dimensions where you have the electronics, the whole electronics, including the metal layers, in just 11 micrometers. Nowadays, we are even using less than 11 micrometers. So the electronics is going more and more vulnerable, in particular to single event effects. At CERN, we are using this we are taking advantage of that phenomenon. But in everyday life, it's a problem. It's a problem. Okay. And this is old technology. Now, Alice, the Alpine chip is in version #3, and we are working in monolithic detectors, as you were aware of, because of the conference past week. Okay, so let's start in the basics. Electronics starts in this device, the diode. The diode is the most useful and the most used device in the world. Everybody looks at the transistor, but the most important is the diode. Why? Because we are using diodes for light, we are using diodes for energy, and also we are using diodes for detection. Okay? Typically, when you are studying electronic engineer, you only understand the diode as a rectifier. But the rectifier is not by far the most important function we use with the diode. This is a LED, okay, and this is a typical, conventional monocrystalline solar cell. Now we are covering square kilometers with diodes. So, which is the magic of the diode? The magic of the diode, this is from the first courses in physics, is basically an opposition. Okay, in the depletion volume, you get a fight between the drift current coming because electrons and holes are attracted by the electric fields inside, and the diffusion current. So diffusion current because one side has more electrons, the negative part, the N part, and the other has less electrons, the positive part of the P side. In the equilibrium, we get magic because in the equilibrium, because of the equilibrium of those two currents, we will have a built-in electric field. Extremely huge electric field. I'm speaking about more or less 100, even 100 kilovolts by centimeter, or even 1 megavolt per centimeter. So yeah, it's extremely huge. It's extremely huge, yeah, because the voltage is not big, but the thickness is very, very thin. We're speaking about micrometers. So if you divide, for example, 1 volt between 1 micrometer, you get 1 megavolt by meter. So it's very critical because that's where the magic starts in the case of the diode. You can use the diode to get light, to absorb light. Then you will generate electron-hole pairs. And because of the built-in electric field, the electron and the hole will follow different paths. So they can be collected in the electrode. So basically, you can use the diodes as a source of current. The source of current we need to feed our electronic system, even our cars. If you are interested in detection, this is a kind of detection, but here the point is to increase the efficiency of conversion, not to increase the amount of things we can look at. But if you are interested in detection, the next step is the photodiode. In the case of the photodiode, this has no bias. The photodiode needs a bias. Why a bias? It's a reverse bias to increase the volume of the electric field, because it is the electric field that is responsible to avoid that the electrons and the holes recombine. Okay? And in the extreme case of particle physics or nuclear physics, we use P intrinsic N devices. Here we have a crystal to increase the amount of electrons and holes created by the ionization process, because this structure is able to detect high energy particles. So think about that humble diode that we are using just to rectify 100 years ago. Nowadays, it's the most used device. This is the other most used device, a MOS transistor. If you look with attention, here you have a p-n junction. There you have another p-n junction. And on top, you have a capacitor comprised of silicon dioxide, a dielectric electrode, and silicon. So the point is, when the device is not working, to avoid any electrons, any path of electrons coming from one diffusion island for the other diffusion island. Why? Because that diode and that other diode is shunted off. Okay? It's biased. You bias the device to avoid any current going to the volume, because you want to control the electrons coming from here to there using a very small electric field in this structure, in the capacitor. Typically in electronics, we speak about a channel. We have a threshold voltage to the channel, and we are extremely worried about the quality of the conduction in that channel. But take into account that that channel has only typically between from 10 to 50 nanometers. So this is a very shallow device. The current is very shallow, okay? And the problems come when this device is not conducting through the surface, okay? But through the bulk. This is a detail coming from a US journal of the track of a particle. And you see that the electric field is following, it's a plasma column. The electric field is following the track. So basically, you are totally altering for a flickering moment, you are totally altering the behavior of that device. This is a single event effect. In particular, you are using this PN junction as a non-intended detector. Remember, when you want a detector, the diode is reverse biased. So basically, what the message for you is that in any MOS device, you have two parasitic detectors. So this is vulnerable to transient ionization. The name in this business of transient ionization is single event current. But we are vulnerable to more effects. One, very important in the case of diodes, is vulnerable to displacement dose damage. What it is displacement dose damage? We are using extremely pure crystals, 99.79% of pureness to have a crystal, a silicon crystal, with a conduction good enough to make transistors. Okay? So if you cross particles or even gamma photons through the Compton effect through the crystal, you are destroying the crystal. Remember from the classes you took that you have a valence band and a conduction band. That's a very simplified image of the structure of this conduction mechanism in the momentum space. But to have that very simplistic behavior in the momentum space, you need to have an extremely poor, well-ordered crystal. If not, it's impossible to have a conduction band along the whole device and a valence band across the whole device. So we are vulnerable to displacement dose damage. Not extremely huge in the case of MOS, because remember, the displacement damage is basically made in the bulk, and the device is functioning in the shallow. Okay? Another vulnerability, total ionization dose. We have a lot of oxides. The first oxide we have is depicted over there. It's not depicted in this simplistic picture, but this is one transistor, and we use billions of transistors. So we need some trench to isolate any shallow current from this device to the neighbor device. In particular, the MOSFETs are in a castle, surrounded by a wall. A wall of what? A wall of oxide. An oxide is a dielectric, okay, but you also have solid state ionization in a field oxide. You will create holes and electrons. Electrons will find a path for leakage. Okay, in 1 millisecond or a couple of milliseconds, they will go away. But holes in an oxide, the mobility of a hole in an oxide is basically nil. Why it's important? Okay, everybody works with flash memories. This is a flash memory. The inner workings of a flash memory is precisely the storage of positive charge in the oxides. Okay? You have also an oxide establishing the dielectric here between the gate electrode and the silicon, and also you have manufacturing oxides, dielectrics in particular. Dielectrics that are useful when you are in the foundry putting a layer over a layer of material to grow the device. Okay, so take into account that the dielectrics are there. Dielectrics are able to store electric charge, in particular positive electric charge. For a device that is controlled by electrostatics, it's very important that the electric field is controlled here, but you will have electric fields there, and even electric fields without your control there. They will affect the device response, in some cases, very dramatically. Okay, so our technology is wonderful for information process, etc., but it is also very, very fragile. Everybody here knows about ionization dose units. This is a typical number of pairs. Typically, in these fields, instead of the gray, we use the rad. Okay? Why? Because commercial electronics, the electronics we use every day in, I don't know, in domestic machines at the kitchen, starts to fail more or less about 100 kilorad. Okay? So typically, we prefer instead of 1 gray or 1 kilo gray, we use the rad. But it's only a matter of get used to. It's the old unit. This is the electron-hole pair creation energy in silicon dioxide. It's important because one of the main issues with the oxide, in particular the silicon dioxide, is the accumulation of positive charge due to irradiation. Just a thing to consider, we use silicon dioxide because we can grow silicon dioxide on top of silicon. Okay? That oxide is attached to the silicon bulk. There is another problem that was discovered 20 years ago. It's a radiochemical effect. When you want a very thin oxide, today oxides are made 2 nanometers or so, okay? But when you want a thick isolation oxide, the trick in the foundry is to add water to the silicon oxide, the oxide. It has exactly the same minute amounts of water, okay? The oxygen will go away, but the hydrogen will stay in the quartz, in the silicon dioxide. It's exactly the same principle that we use to make a cake, or bolacha. In the case of a cake, the gas responsible of getting a spongeous cake is carbon dioxide. In this case, the gas responsible to make a spongeous oxide is hydrogen. But when you irradiate a device, that hydrogen also gets energy enough to start to diffuse in the oxide. So, when you have diffusion, at the end, anything in diffusion in a bulk will go where? Will go to the surface. And remember, we have a particular critical surface. It is the surface where we are building the channel. So at the end, remember, this is our critical surface. Consider hydrogen going everywhere in the bulk. If it goes to the field oxides, no damage. If it goes to the bulk contact, no damage. But if hydrogen comes over there from the oxides, then you have a problem. Which problem? The amount of traps you have in the channel. Which is a trap? A trap, as the name implies, is localized asymmetry in the crystal capable of taking an electron and stopping an electron, capturing an electron in the trap. Or if you are using a P device, capturing a hole. Okay, so they are interrupting the channeling of charge from one diffusion island to the other diffusion island. In the case of an MMOS, the oxide traps, the traps you get in the oxide, grows very fast. The interface traps grow more slowly, but at the end they encounter in the interface. So in the case of MMOS, at the beginning, the MMOS is even better with a little amount of dose. In the case of PMOS, both oxide traps and interface trap goes in the same direction, interrupting the channel. Okay? If you continue ionizing or giving ionizing radiation to the device, then that beneficial effect at the beginning of the MMOS will go astray, and then you will also destroy the capability of the MMOS to conduct electrons through the channel. TID, that's the name of this business. Total ionization dose is due to the creation of electron pair because, that will cause long-term effects in oxide due to hole trapping in the dielectrics, and in particular interface traps in the channel. Okay? The most critical problem is the interface trap due to oxide radiochemistry and also due to the movement of the holes, the diffusion of holes in the oxide. In thick oxides, bigger than 5 nanometers, this is a problem. Nowadays, we only use thick oxides in the trenches. Remember, you have to isolate the MOS transistor from the other neighboring MOS transistor. So this is a problem for the isolation, the field oxides, isolation oxides. In very thin oxides, less than 5 nanometers. Very thin oxides are typically in the gate. Only interface states are important. Okay, that's the business today. This is typically the current, the drain current coming, the effects. This is the drain current in saturation of a MOSFET, okay? And those are the parameters typically affected by the TID, the threshold to establish the channel, and also the conductivity. In that case, this is electrons. In that case, the electron conductivity, if you are using an MOS, or the hole conductivity if you are using a PMOS, okay? There is another effect I will show you in a moment. This is just a cartoon of the whole picture. You will have accumulation of positive charges, then you have affecting the channel because of the traps, and also you will have leakages of electrons due to the excess electric field, leakages going to the bulk. This is not a problem in the case of a conventional MOS, but it could be a problem, is a problem in fact, in the case of silicon oxide isolation, another technique typically we use to avoid single event effects. Those are just how every effect is affecting the threshold voltage, and this is the threshold, the affected threshold voltage, this one, from the physics of any MOS. It's not important. The point is that we have new terms, the interface traps and the oxide traps, affecting the threshold. Remember, if your bias voltage is not going over the threshold, you have no channel. Without channel, you have no interrupting transistor. Okay? This was a negative effect, but it could also be used for detection. Those are RAFETs. Okay? RAFETs come from Ireland because they have the patent from the Tyndall Institute. This is the N-MOSFET threshold voltage. You see the combination of the two effects. At the beginning, the threshold voltage is going down, but when the interface traps are dominating, you will have voltage increasing up to the point that you are not able to open a channel. In the case of PMOSes, this effect is always going there, there, and there. So you can use PMOSes, big PMOSes, as radiation monitors for those. Typically, it's the radiation monitor you have here, or in your hand at CERN, or at any hospital, or even here in nuclear facilities like the one we are in. Okay, this is, you can buy that. Even we have mounted in a satellite this, not this, the next one in the catalog, but this is to show that the bad effect in microelectronics could be used for the good in the case of detection. The other thing is leakages. This is the most important part in nanoelectronics today. Up to now, we have been speaking about one single transistor. But what happens is we have several transistors, okay? Then your capability to control currents through the gate could be good enough. But remember, we have here phylloxides. Phylloxides that are responsible of making a wall around any transistor to avoid precisely leakages, natural leakages, from one transistor to the neighbors. Okay? But if you get a huge amount of charge, positive charge in this phylloxide, consider you have a metal gate on top. So basically, you are making, without noticing, a lateral transistor. You will open a channel from your source to your drain without noticing, because you are not commanding a channel, an open channel there. This is a leakage. We typically represent leakage with a parasitic transistor associated to the main transistor. By far, this is the most important problem today. Even we can remember is integrated microelectronics, so due to this effect, we can have inter-device parasitic channels. Here you have a NAND gate, a NOT gate that is feeding the next NOT gate in a combinational whatever. Okay? And in this case, this gate is activated because of the leakage without giving the order to command, without a signal, without a command signal. There is a technology with a barium oxide. This is the SOE technology. Typically, we use SOE technology to get very thin devices. Very thin devices are less prone to single event effects. But the bad news from SOE is that you are more sensitive to TID. Okay? So if you are in an environment, in a technological environment or natural environment where TD is a problem, SOE is not recommended. If you are in an environment where TD is not a problem, total ionization dose is not a problem, but single event effects are a problem, then this is the technology to follow. You have to take care of. Why? Because if you don't have a lot of substrate, the amount of electron and holes you create from the ionization track is limited by your design. Okay? But remember, in the barium oxide, you will accumulate positive charges. So at the end, you are disconnecting your transistor from the ground, and your transistor is floating on top of a capacitor without your control. So those are, at the moment, those are the main problems in the case of TD in modern technologies. I can elaborate about in Wednesday or in Friday if you are interested in these kind of things. Okay, let's go to a real situation. We decided to start a new collaboration at CERN. The RD53 collaboration started in 2013. It was closed down in 2023, 10 years for developing a new readout chip in extremely harsh conditions near to the collision points at every experiment, particularly in Atlas and in CMS, but this technology is spreading nowadays to every experiment at CERN. So for us was at the beginning. This was at the very beginning. I'm speaking about meetings we had at the end of 2013 and at the beginning of 2014. I was very young there. Okay, so in principle, to go to 65 nanometers looked as very good news because the dielectrics in the gate were extremely thin. So the only thing to worry about was about leakages. You can avoid leakages just to avoid the metallizations on top of the trench oxide up to a point, and to avoiding the use of silicon on insulator. Bad news. This is from Giulio Borghello, one friend of mine. We have several papers, one paper in common, but I have working with Giulio, that presented in previous meetings the bad news. Sensitivity to TID decreases with the gate oxide thickness. So a 65 nanometer transistor with only 2 nanometers of oxide in the gate have to be very radiation hard. As a general rule, increasing miniature means decreasing TD sensitivity, but increasing single event effect sensitivity. That was the textbook recipe in that years. Bad news. The bad news were 2014, at the very beginning of the RD53 collaboration. We detected effects. This is the whole picture of a transistor. This is the ring of the shallow trench isolator. And also, you can see in the micrography, this is the gate. The gate oxide is that thing, but it is surrounded by another dielectrics, silicon nitride. Silicon nitride is critical during the foundry process because you have to isolate one layer from the next one, and you have building different structures to construct the device. So that silicon nitride was there in the very beginning, and it will be there during the lifetime of the device. Also, doping profiles were critical. We discovered the hard way. We chose 3 technologies, one from Samsung, not exactly from Samsung, but from another Korean company. I'm in YouTube, I will not say the name, okay? Another one from Global Foundries in the US, and another one from the TSMC. TSMC nowadays is the total dominant, the total boss of the market, so I will not make a publicity of TSMC because everybody has TSMC in their pockets. So talking with the foundries, they basically said to us nothing about the doping profiles of those shallow trench isolator oxides because they are doped. Doped, why? Because during the process, you get leakages not in a natural way. So it's in a paper with Giulio. We build exactly the same structures with 3 foundries, okay, non-disclosed. And from that study, we concluded that TSMC was the best one. But it took 2 years to discover that effect because the foundries are very close about their process because it's huge. It's a huge amount of money in these tricks of the trade. Okay. That was the bad news coming from Giulio and from the advisor of Giulio, Federico Faccio. Federico is the top dog in the TID, at CERN and in knowledge. Basically, everybody in the field is learning from Federico. So we detected a huge performance degradation due to radiation effects in 65 nanometers. Not only this is the variation in the maximum drain current. That's the drain current when the device is in the on state. So you can see that between the pre-rad and the 1 gigarad, there were extremely big difference. I have to say that 65 nanometers was chosen that year because RD53 wanted, and we got 10 years later, wanted to withstand, the chips from RD53 wanted to withstand 1 gigarad of total ionization dose. It's equivalent for the high luminosity LHC, more or less 2 years of operation in the inner tracker. So basically, yeah, the caducity of the inner tracker is 2 years. After 2 years, you have to, we made the jets, you have to stop basically everything, take out the device, it's not cheap, okay, and replace with another. I will elaborate about in quinta-feira, okay, about this particular thing. Okay, so why such a large degradation? Several oxides presented in CMOS technology, as I said before, not only in the gate oxide, much thicker than the gate oxide, and with a lower quality with respect to the gate oxide, because basically those are ancillary oxides. Oxides not used to control the device, but to isolate the device or to build the device. This is another cartoon of a real 65 nanometers device. We have the polysilicon gate, that the dielectrics for the capacitor closed by that electrode. That electrode is the p-doped substrate. This is more or less 2 nanometers thick, so here we have no problem at all, but we have problem with the spacers, silicon nitride, with the shallow trench oxides. And you can ask to me, why do you cannot take away those silicon nitride spacers? If you build a naive diffusion here, the electric field there is so huge that the device will destruct by itself the very first moment you connect to the bias. So we have to reduce the amount of electric field here using a low-doped area. That low-doped area is built thanks to the silicon nitride, because the silicon nitride is the mask we use in the foundry to build that LDD area. So you cannot take away, you cannot withdraw that silicon nitride. It's critical. Consequences. Those are small w, small l, large L. W is this length, L is that length. So those are the typical parameters we use to design a transistor in microelectronics: the thick, or the width, and the large. So after a lot of analysis, here we have a recommendation to us as a designer: avoid any small w, avoid any small l. The small l was not big news, because every analog designer avoids the small l. But if you are a digital designer, you are interested in having the small l and the small w. Okay? Typically, in the field is named string 0 standard cell. So we had to define our digital cells. When you have an analog design, it's up to you the design. You design, you put in one transistor, sizing this transistor, sizing the other. You have basically control of everything. When you are designing in the digital domain, because you have to repeat a lot of structures, typically in the millions, okay, it's impossible to do by hand the standard cells, the digital cells. So you use standard cells well proven by the foundry. In that case, we discover, for our disgrace, that the standard cells have to be ASICs, specific made standard cells. So that delayed the device another 2 years. Anyway, standards. I was just telling to you our miseries in RD53, but the device is now working. Okay, the device is now being installed in CMS and Atlas. It's working perfectly if you get a refrigeration of minus 15 degrees Celsius. At room temperature, the device is not working up to 1 gigarad. It crashes at around 500 megarad or so. But sometimes the solutions comes not from microelectronics, but just put in a fridge put in a fridge. Okay, it's more simple to say than to put the fridge. So this problem of TD is so old that we have standards. Okay, the standards from the European Space Procurement Organization is the ESCC 22900, Total Dose Steady Irradiation Test Method. You have an expert in that particular standard here, Sheila Marcillet. So, and you have to, this standard is taking the military standard, the ACTM, and another military standard. So basically, you have to make an initial measurement, you make the dose irradiation, make an interim measurement to know how things are evolving in the device. Take a lot of care with your temperature, because remember, holes are mobile, not big mobile, but are mobile. Electrons are big mobile in a dielectric, so annealing is extremely critical, because the prompt TID effect is not the same as the late TID effect. Even if you have to take your measurement in one lab and take your device to another lab, it's like with the food. You have to maintain the chain of cold from one side to the other, to have the temperature control, to avoid holes escaping, and to have another effects not related to the radiation you make. Okay, and the final measurement. It's very simple to say, but you are aware it's not so simple to make. Okay, those are typical facilities. The break will be at 15. The coffee break will be at 15. No, okay. I'm wonderful. Okay. Here you have different facilities. You have one here in Brazil, nearby, in Universidade da FEI, your laboratory. Okay. Using typically X-rays, electrical generated X-rays. This is very important. We have several in Europe. For example, the Aragor, I don't know the name of your particular one, but yours is in the state of the art. Okay? If you don't have money for an X-ray, you can use the poor X-ray source using iron. Okay? It's not. It's important because you cannot, when you are mounting things, you cannot take your Aragor to the tunnel. So we use this. Just to be sure that everything is going well during the installation. If you want, I don't know, to make an invasion of the moon, you use this huge monster. It's Naiade. It's a pool type where basically you are reproducing the effects of a small nuclear bomb. It's in Madrid. Okay? And in Sevilla we have an accelerator facility, the National Center of Accelerator, where we mounted a cobalt bomb from one hospital that we modified, and basically it's satisfying it's fulfilling the standard 22900. So this is one of the most used facilities at CNA because, in fact, this was it was paid 50-50, 50 by the government and 50 by a company. Alter Technologies is a local company responsible of certification of electronics for space. So this is one of the most used facilities in Sevilla, even more than the accelerators, because it has a lot of commercial interest. Even companies coming from France and from Italy, all of the companies related to medical instrumentation, to take into account the radiation in the medical environments, and from space are using this thing. Okay, this is just the cobalt spectrum, 1.17, 1.33, and here in Brazil, because I was lucky enough to collaborate with you, we discovered that it's not the same to irradiate with X-rays that to irradiate with gamma. And the main reason is that with X-rays you don't have Compton effect, and with gamma rays you have Compton effect. Yeah, when you push the electrons due to the Compton effect, those electrons will also make radiation damage. So if you are interested in a probe to test only TD, remember, for microelectronics, TD is the most important thing. Those damage, crystalline damage, is not important because the channel is very shallow, very narrow. So if you want to test only TD, then you have to go to the X-rays, okay? Not to the gammas. Because in the gamma, the effect is combined, and you can show the papers later on. Because we were studying that effect, it's Alexis was the PhD, now he's a postdoc, that made those measurements using gallium nitride, not silicon, but gallium nitride power transistors. Okay. Life is not simple. Everywhere is aware of. Remember about the hydrogen? Okay, that hydrogen has an effect to the low dose rate sensitivity. You have your facility, so why not? You are making accelerated aging test. That's what you are doing with the TD, and you take the knob up to the maximum. So the dose rate is huge. The amount of time you are devoting in black and obscure lab is diminished, and you can go outside for a coffee or for a beer. Wonderful. No, not wonderful. Why not? Because if you use a low dose rate, the hydrogen has time enough to diffuse from the point of liberation to the oxide interface. That's the enhanced low dose rate, because in reality, irradiation is a slow process. It is not a fast process, okay? So again, in our case, in RD53, we discovered that the hard way. And we were during a full summer in Croatia, Zagreb. That was the reason I was working with the people from Zagreb, Croatia. Using the gamma radiation facility. It is a gamma radiation facility coming from the Soviet. It's underground because it's huge, it's a monster again. But the experiment was to know if RD53, the RD53 chip, was sensitive to this effect. It was. So that was responsible to build RD53C, the third version of the chip. Take into account that one chip is not for free. One chip is around 500,000 euros. That's the cost of a chip. You don't notice that effect, that cost, in everyday life because we make chips by the billions. So you share the cost by the billions. But when you are making ASICs, application-specific integrated circuits, in low batches, you have to pay a lot of money. So when I say discovering a thing the hard way, is the hard way and the pocket way. Okay, so be aware of the enhanced low-dose ray sensitivity, because in space and also in applications, TD is a slow aging process. Okay, more radiation effects in electronics. If you are tired, we will make the coffee break. Okay, it's up to you because I have been speaking about TD, so in the audience, in YouTube or whatever, if you are interested in any questions before the... Eu entendo el português. Não falo bom, mas eu entendo o português. It comes, this hydrogen, because it is not a proton, it's an hydrogen combining with the silicon dioxide, okay? It's a radiochemical effect. This is coming from the foundry. Remember, we wanted thick oxides, so the trick to get thick oxide is put hydrogen inside. It's like the effect of the carbon dioxide in a bolacha, to get a big cake, okay? Levadura.
Vou fazer comentário em português para melhor para os estudos. Seria bom comentar. Desculpa. Rogelio, seria bom comentar, já que o Medina perguntou sobre o hidrogênio, que ele é o responsável por poder criar armadilhas durante a radiação, apesar de não ser por defeito cristalino, exatamente porque eles já estão na estrutura, só que os defeitos criados por eles são rasos, certo? Então, muitas vezes, não tem efeito.
One of your students, Ana Victoria, has detected this same effect in power transistor, in a commercial power transistor. And he was totally lost about the effect, because he was calculating the dose, he was calculating the amount of traps and the amount of oxide charge in the oxide, and the math were not following the effect.
Rogério, eu queria saber por que o Compton, quando você mede com gama, é um problema para você medir TID.
It's not a problem, okay? It's a problem if you want to take into account only the TD effect. But if you use gammas, you will have TD and displacement damage. The displacement damage comes from the Compton electron. So it's not I'm not speaking at the moment about physics, I'm speaking about the standard 22900. If you want to analyze with the standard, because that's the standard you have to follow to certify your device for space or whatever, okay? Don't use gammas, because there is a cross effect between the Comptons and between the photons. The photons are responsible for the ionization accumulated in the charges. The electrons, the Compton electrons, are responsible for the traps excess in the channel. Okay? So you want a clean probe to analyze TD, don't use gammas, use X-rays. And it was demonstrated. That work started, I remember, in a Radex years ago, probably in Sevilla in 2011. Yeah, because that was when I meet you. I was discussing with you specifically when you were interested. Yeah. So in those years, people were working with gamma and X-rays without distinguishing between them. But she was the one following that path to disentangle gamma effects from the X-ray effects. So I think it's important to declare, because it's science here made in Brazil with a little amount of Sevilla. Last question. If not, I will free you for the coffee break and some bolacha.
Yeah. Yeah, we can have a break, a 10 minutes break, it's okay?
10 minutes, okay?
Okay.
Thank you.
Right.
¿Te gustó?
Sí, mucho.
¿Tienes la computadora aquí? Ah, pues entonces. Well, let's retake the course in a minute. I will answer to the very last question from the online audience about the effects of annealing. As I said, annealing is a double sword effect, or double-edged sword effect. At the beginning, annealing looks good because, you know, due to the diffusion, thermal diffusion, you will have traps away from your zone. But after a couple of hours, precisely because of the same thermal diffusion, the traps created in the bulk will go to the surfaces. So you will discover that your device that in principle was recovered during the first minutes during annealing in your lab will be even worse several hours after the irradiation because of the detrimental effects of deep annealing, deep traps. Okay, so in any case, avoid annealing. For example, in particular at CERN, in the RD53, we have to ensure that during the 2 years of working, even if there are no collisions, the temperature has to be at minus 50 degrees, precisely to avoid any detrimental annealing effects. So annealing is not good to decrement the TD. It's just a false friend. That's a take-home message with annealing. Okay? Well, let's go to displacement dose damage. Displacement dose damage is not critical with the exception of that effect related to detrimental annealing. Okay? Displacement dose damage is not the first effect to consider in most electronics because most electronics is very shallow. But if you are doing, as you are starting to discover, if you are doing power transistors, the channel is through the bulk. So in the case of power transistor, the damage in the bulk is important. Okay, but that's a particular effect in displacement damage, a very huge amount of 1 MeV neutron equivalent fluence in power transistors. At the moment, in this very basic course, I'm speaking about signal transistor, okay, because I have to start, electronics is huge, so I have to start from one point in particular. So where it is very noticeable, the damage, back to the diodes, okay? Why? Because a diode is basically a bulk device. Remember, a diode, when you are using diodes inverse or reverse biased diodes as detectors, basically this is a solid state ionization chamber, and the creation of electrons and holes is increased with the amount of thickness, with the amount of bulk you have. So if you are damaging the bulk, you are damaging the charge collection efficiency of your device. This was considered from the very beginning. This is a couple of strip sensors from the ATLAS experiment at the very beginning of the LHC program. Okay, so this was considered. In fact, we had a full collaboration, the RD50 collaboration. I belong to the RD50. RD50 lasted 20 years, so I was there since 2012, at the very beginning of my career at CERN. Nowadays, RD50 is overlapped with DRD3. It's the next name, but it's the same question, because radiation damage in detectors was important from the very beginning. Okay, in fact, we had, I was not born, not even born in those days. Before RD50, we had RD48. So it has been a worry at CERN since the beginnings of the detector technology using silicon. Okay, and even we developed several recommendations now in FORCE, in FEMES, and in ATLAS, but not there. In particular, those were P in N silicon. So basically the substrate is N, is negative, and the device, the doping, is made on P. Okay? Nowadays it's P on N. Even we don't use the Krochalski method, conventional to electronics. We use the float zone technique because with depleted float zone, I'm speaking about the building of the crystal, the very beginning of the electronics, okay? It has, we can control the amount of oxygen. And oxygen is very important to avoid the diffusion of vacancies and defects in the crystals. So from the very beginning, we have been making defect engineering in the detectors. Okay. So this is a detector, typically a detector. Those are the readout chips in a strip coming from Atlas. This is an approximate cross section of those diodes. Remember, a strip is a diode that long. Typically, we use double. We use one in that direction and in the back, another in the other direction to get X, Y, Z, in particular X, Y location. So the point is that the particle track has to basically respond in the device through the Coulomb interaction. The amount of energy you need in silicon, the medium energy, is 3.6 electron volts, but there is a small amount of energy, the non-ionization electronic energy, that goes to destroying the lattice. Okay? It's typically between 1% and 2% of the amount of energy you put into the track. So 98% in the worst case is going to ionization, and 2% in the worst case is going to destroy the crystal. We have to avoid in that case the effects coming from the destruction of the crystal, because you will destroy the crystal at in any case. Okay, it's just a run against time. So, sorry. Okay, to compensate this effect, we have to increase the bias voltage. This detector starts to have this particular one with 300 micrometer thickness. In microelectronic industry, we have basically two thicknesses, 700 and 300. Okay? Beyond that, you have to pay a lot to get different crystals. And the size of the crystal, the transversal size of the crystal is typically 6 inches up to 10 inches. Okay? And a pure crystal of silicon is more or less from this side, from this floor to the ceiling. And you cut the crystal in slices to get to build in those slices, wafers, okay, the detectors. So the point, the first defense against damage is to increase the bias. Up to what? At the beginning, you can start with a full depleted device at 100 volts. Our maximum in the long shutdown, in the first era of the CMS and Atlas, was 600 volts. So this 600 volts is the maximum amount of bias voltage the device can withstand to compensate up to a point the damage created by the particles. Okay? The other thing you can do is to reduce the temperature. Why? To reduce the diffusion effect of the traps. That was tested in CMS and in Atlas in our labs, not in the detectors, during the last 8 years or so, and nowadays it will be standard. So CMS is a big fridge. In particular, the tracker in CMS is a big fridge. Okay? And Atlas is exactly the same. They will operate at minus 50 degrees with carbon dioxide fridges, precisely to avoid that thermal diffusion of the traps. Okay. The name of the business here is the Hamburg model. The Hamburg model was the PhD work of one of my best friends, Michael Moll. He's the responsible of the solid-state devices laboratory. Is where I work every summer, if I can. If you don't call me to come to Brazil, I'm there, or I'm teaching in Sevilla, or I'm living in Geneva, in Michael's small lab. In particular, this was for Michael's course 6 years ago in Sevilla. Okay, so that's the Hamburg model. This is in green is the LHC amount signal in comparison with the flux, the fluence of neutrons. For radiation damage, the probe is neutrons. Why? Because you have no Columbian effect. You have no direct ionization effect. Okay. Neutrons calibrated at 1 mega electron volt maximum energy. Why? Because at 1 mega electron volt, those neutrons will not generate a lot of nuclear reactions in the silicon. This is basically a matter of which are the nuclear cross-sections of neutrons in silicon. They start at 4 MeV, okay, for turning silicon into magnesium and then turning silicon into aluminum. So typically, the probe, if you want to have a test facility for this kind of effects, typically you have a trigger reactor, or the reactor you have here at the pen, and you get 1 MeV neutrons using a cesium, I guess, a cesium filter to avoid neutron energy beyond 1 MeV. I think it's cesium. Okay, it's a cesium window. I'm just remembering. If not, we can test the details later. So from this analysis, this is P in N, and this is N in N. We decided to select P in N using one particular procedure, floating zone, and controlling the amount of oxygen. That was the result of the RD48 collaboration plus the first years of the RD50 collaboration. Nowadays, the float zone silicon oxygen control is the standard for the long shutdown, the upgrades of the Atlas and the CMS. And we are happy that our work in the previous years is now useful. So we have, using this defect engineering, we have increased the amount of radiation tolerance of detectors in a factor of 10, 1 order of magnitude. Without that, it's impossible to go to the upgrade, to the high Lumi upgrade. Okay, so in principle, it was good to know that our effort was useful. Which is the physics of displacement damage? Okay, particles, wherever they are, transport energy, sure, but also momentum. Okay, and the point to consider is momentum. We have to consider collisional mechanics in crystalline structure because you will create lattice damage. Basically, you will have a primary knock-on in one silicon atom. You will displace that knock-on. That effect, it was very noticeable in past meeting of Brazilian physics during the spring, that this very effect is the one they are using to detect coherent neutrino scattering in CCDs. But for us, it's a nightmare. Okay, for them, it's the main signal because this vacancy typically has a ionization effect, secondary ionization effect in the kilo electron volt regime, very hard to detect, but neutrinos in the coherent scattering are responsible of that effect precisely. But for us, it's a nightmare. Okay, so you will have a vacancy and a hole in the lattice, and you will have an interstitial because that silicon atom, that silicon nucleus, has to go somewhere. In that case, you are destroying the lattice. Okay, you can have isolated defects, vacancies and interstitials diffuse. The name is stable defects. If they recombine, no problem, you have a bad quality crystal, but you still have a crystal. But if not, you have a Frenkel pair. And the Frenkel pair are the responsible to destroying the properties, the good properties of that solid state ionization chamber. Using, if you are bombarding with electrons or protons lower, with energy lower than 10 MeV, you have Rutherford scattering. In the case of Rutherford scattering, your defects are isolated one by one. So you can withstand. It's typical, the typical defects when you are using electrons in a medical accelerator. okay, because your detectors will be destroyed by point defects. But if you have neutrons and protons beyond 10 MeV, hadrons, okay, then you have cascades. It's very important. A low energy proton goes into the crystal with a bias because the electric field of the proton is going in front of the proton. But when you go to relativistic energies up to 800 MeV, the electric field of the, because of the contraction, the Lorentz contraction, the electric field of the proton is pancaked. So basically, the proton, you will see the proton in front of you like a neutron because you have not a bias coming from the electric field because it's totally compressed. So in that case, typically we speak about hadrons. Okay? Why more than MeV? Because protons with more than MeV are capable of making nuclear reactions. There is no nucleus with a Coulomb barrier bigger than 10 MeV. Above 20 MeV, in elastic collisions, nuclear reactions are responsible of all defects. Nuclear reactions, we tested at CNA because one work with Alexis, exactly. In the case of inelastic collisions, this is a fancy term to say that you are generating ionization inside the device because of nuclear reactions. And we are not speaking about kilo electron volts of ionization. We are speaking about mega electron volts of ionization because the first reaction are exothermic. So basically, you are creating not only damages, but also ionization at the same time. For that reason, we tend to avoid neutrons beyond 1 MeV to analyze crystalline damage, to avoid any cross effects coming from nuclear reactions, etc. In the case of 1 MeV, the probe, the threshold for creating a Frenkel pair without recombining is 21 electron volts. So this is the typical a silicon atom recoiling after a 50 kilo electron volt event. And you can see that at the end, you can have a percolation of the crack, because that's a crack, in the crystal. In the case of that crack goes from one side of the crystal to the other extreme of the crystal, your device is destroyed in a burn. Okay? It's a very rare effect, but sometimes happens. When you irradiate a lot, in RD50 we irradiate a lot to know the limits. Okay? We have seen, very wonderful to see, devices burn from the inside and popping out in a crater. Okay? Because of this cracking, electrical cracking in the crystal. Okay? So, the final concentration of defects depends on the total energy that goes into displacement. Not exactly 0.1%, typically in the worst case 1%, in the case you are in the high energy physics. Okay, there is no dependence, it's under discussion, on the type of initial energy of the particle. This is the Niel hypothesis. And we know, because Veronica, another student from Czechia before, Veronica in our group at CERN is studying the limit of precisely that effect, the Niel effect. So not only you are studying cross-reference, cross effects, but also us in the case of displacement. Okay, so we found, in particular Veronica is reporting, that there is a dependence on the type of initial energy of the particle at very high energies in that case. So neutrons are not exactly the same like hadrons, protons at relativistic speeds. Okay, so the number of displacement Frenkel pairs is proportional to the primary knock-on energy. This is the typical amount of the calculation, a handkerchief calculation, or an envelope, back of the envelope calculation you make at the beginning to know the amount of Frenkel pairs you have in your device. Sorry, one question. No, it's exactly the opposite. It's exactly the opposite. You will have cascades, not point defects, at high energies. not at low energies. Why? Because the primary atoms will be, the amount of primary knockout atoms will be huge. In the case of one electron, or in the case of a gamma due to the Compton effect, okay, typically you have one Frenkel pair per photon, or one Frenkel pair, or a couple of Frenkel pairs per electron. But in the case of an hadron, or in particular a high energy neutron, you will have cascades of primary knock-on atoms, because the hadron will collide not with one nucleus of silicon, but with several. And then you have a cascade because those knockout are energetic enough to get new secondary knockout. Yeah, but again, high energy hadrons are responsible of cascades. Low energy leptons or high energy leptons or high energy photons are responsible of point defects. It's very clear when you go to the lab. At energies, considering energies from cosmic rays or considering energies typically in the collision environment. When I'm speaking about the collision environment, I'm speaking about from the collision point, I'm speaking about more or less 40 centimeters from the collision point. But 40 centimeters of the collision point is the most interesting place to put detectors at the LHC, because you can make vertexing and you can detect extremely high particles with extremely high decay time, with very short decay time. Okay. So this is precisely the Nile hypothesis. Well, more or less, protons up to the point of 20 MeV are more or less the same effect like neutrons. The standard is neutrons, and this particular area is being reconsidered by our students in the group. Okay? It's approximately true. So as a first step, you can consider that relativistic protons and neutrons, high energy neutrons, basically make the same damage in silicon. This is just math to consider. The point is in the Linhart partition factor that is responsible to distribution and the angular distribution and energy distribution of the knockout atoms, or the knockout nucleus. Okay, so in principle, we still use the Neal hypothesis, but I have to insist that it is under consideration. Okay, damage units, just for you to when you look at the slides at home, just to have some relation between the displacement damage dose, the amount of dose you put in your device, with the damage, typically with the damage factor that translates between dose and real damage. Okay, this is just to consider it's a detail, considering a normalization for operating with protons, operating with electrons. This is precisely the Neal hypothesis. Okay, just to consider a normalization related to other kind of particles, or for a spectrum of particles, as I found in space. That's the typical damage integrals we need to make, considering the whole spectrum of energy, and sometimes even the whole geometrical angles. Okay, so this is the method used for displacement damage dose. Those are the measured data. This is the Neal hypothesis. So using that factor to have data from protons to translate to data from neutrons, we got from combining this, we make that magic. Okay? It's only approximate. So the correct name is magic. But it's not exactly, but it's useful enough in the industry. For example, Messenger, he is an expert. Messenger is one of the creators of drugs, one of the programs in the field. So in that case, this is gallium arsenide and germanium, considering one sun in low Earth orbit for a I will say, displacement damage in photovoltaic cells in satellites. Okay, because this is typical. Yeah. Everything is not about CERN. At the end, when you put a satellite, the most vulnerable diodes, detectors, is the huge surface due to the photovoltaic devices. So the first thing to consider in space about damage is how damages are my photovoltaic cells, because without them we have no satellite. Okay, so doing a microscopic analysis of the defect, this is a junction, okay, the PN junction. So I was speaking in the first hour about symmetry in a crystal means that in the momentum space you will have a valence band and a conduction band. Basically, this is saying that in a crystal you have free electrons to conduct along the semiconductor, in particular along channels in the semiconductor. If you translate this to the space, to the space image, you get channels in the semiconductor where the conductivity is huge. That's the reason we use basically silicon, crystalline silicon in electronics. If you have a MOS, every MOS is aligned in the crystalline direction 110 if you want to conduct with electrons, and 111 if you want to conduct with holes. So a PMOS transistor is aligned in the 111 crystalline direction, and if you want to conduct electrons in a MMOS, you are aligned in the 110 crystalline direction. So basically, I'm translating to the momentum space this channel conduction that you have in crystals. So basically, to have conduction, you promote an electron from the valence band to the conduction band. This is the area where there is an electric field. It's the built-in electric field. What happens when you are bombarding the device? You will have localized levels. This means that electrons will be captured or will be released depending on the ambient temperature. So your device is not as predictable as a pure crystal. In particular, if your defects are near to the Fermi level, you will have a generation. Instead of recombination, when you apply heat, room temperature, okay? Take into account that the temperature range of operation of a crystal goes from the liquid nitrogen temperature, minus 196 degrees Celsius, up to 125. So it's a huge range of temperature where you have crystalline conduction. Okay? In the case of defects near to the Fermi level, you have leakage. Leakage current for detectors is also named as dark current. So basically, your device is transforming heat into current that you don't want, okay? Because your device is leakaging current, and when the device has to be totally without current. In the case of traps a little above the Fermi level, you have recombination. So the lifetime of your minority carrier is affected. This is important in the case of MOS transistor. Why? Because MOS transistors are a minority carrier device. You conduct with electrons in a sea of holes, and you take out the holes with the electric field applied in the capacitor. Okay? So this is important in the case of electronics. Trapping, remember the Fermi level is more or less here. Okay? If your defects is a bit over or a bit lower than the Fermi, but not in the recombination zone, you have trapping. Trapping is also named as carrier removal because electrons or holes, electrons in that if it appears here, holes if they appears there. Okay? A carrier removal means that your device is very noticeable, the carrier removal, because from the outside in the lab, you start to see telegraphic noise because electrons or holes are trapped into the defects and then released at some random time. So the net effect in the signals is the appearance of a random telegraph noise. That's the origin of the, we discussed in one of our meetings about the telegraph noise. If you have this kind of defects, internal, not once, but several, you have compensation. Compensation is a big problem because if you compensate enough, you can even make space charge inversion. Your device, instead of being an NP, could be a PN. So your diode, instead of being reverse biased, could be direct bias. If you are directly biased with 100 volts, you destroy the device. And tunneling, in that case, this is fun for academics, but is very rarely seen in real devices. Tunneling is good for the audience in the classrooms because it's funny to know, electrons are waves, blah, 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 but this effect is very rare. Also, scattering reduces current mobility, but only a very high frequencies. This is one of the results. Identifying every defect here is still a work in progress since 20 years ago. Okay? That's because we were discussing during the coffee break about DLTS and other techniques to identify the different defects there. Okay, so this is an elaboration of the previous, considering the most important traps in the case of donor and acceptor. Take into account that charge inversion, when you make a whole device, you make doping here. Okay? When you want an electron device, you put doping there. Because to have a positive silicon or to have a negative silicon, you put doping. The effect of doping, one atom every a huge amount of silicon atoms, is exactly this. Is to get traps near to the conduction bands, so an electron will promote to the conduction band at room temperature. You have a negative semiconductor, negative silicon, or you can have an electron here that will be trapped in a shallow defect, an acceptor dopant, so it will create a hole there. So if radiation damage can create fake doping, then you are modifying your device, basically. Up to a point that your device, instead of becoming a PN junction, could be an MP junction, and your device is destroyed. Trapping, shallow defects, etc., and leakage current, level close to MIGAP are the most effective. Okay? There is a whole defect engineering or defect physics where you have to calculate the ionization energy, the concentration of that depending on the fluence, because that's the thing that comes from the outside, from the radiation time with a beam of neutrons, and the cross sections, the captured cross sections of every tap. So this is very similar to the language of nuclear physics, but remember, we are speaking about a crystal 300 micrometers thick at most. Yeah, silicon is very complicated. We have plenty of silicon in nature, but with silicon we can make a lot of wonderfuls like the cell phone you have in your pocket. Standards. Again, there is a lot of standards. In fact, it was one of the very first standards. There is not an ESA standards. Why? Because displacement damage started with nuclear bomb testing in the 50s past century. Because it was the first defect when you have a huge storms of neutrons coming from a nuclear explosion. So basically the standards we follow are from the military standard 883. It's very simple: initial measurement, irradiation, interim measurement, and again, as simple as putting the device in a nuclear reactor to ensure that only 1 MeV neutrons are impacting the device, and after a few hours you take out the device and you take measurements. That's all. Considering annealing, etc. But it's simpler than TID. You have no prone effect here because you are destroying the crystal. Neutron testing is the way for DDD, no charge and efficient momentum transfer by neutron, but they also produce nuclear reactions. This is a hot topic at the moment to study the effects of nuclear reactions in silicon. In particular, my work, I was working in this thing along 2023 and 2024. You are aware of, because I presented in OXE and in the January of 2024, okay? Because we have a neutron facility in Sevilla from our pelletron, Hispanos. This is the typical environment for neutron testing. In the case of thermal neutron testing, I believe that the ITN now is closed because our tests are typically made in Ljubljana, in the trigger reactor in Ljubljana. But sometimes we went to the ITNs. The ITNs is very similar to the IPEN nuclear reactor you have over there. So that's the experimental area. That's the port where you have a filter. I guess it's a cesium filter. That's the electronics. After an hour or so, you take out the device and then you analyze the device. As simple as that. In the case of fast neutrons, that's another history. Okay? To have 1 MeV is not a fast neutron. I know from your nuclear point of view that 1 MeV is a fast neutron, but it is not. Okay? Fast neutrons go beyond 14 MeV, the typical from fusion reactions, deuterium, tritium in particular, and beyond. So one of the things you can make, this was one of my experiments, using an spallation facility. There is an spallation facility. In fact, that was my first experiment where I was collaborating with a neutron time of flight at CERN. And here you can see we were testing different three-dimensional detectors, 3D detectors. This is the electronics to take the signals. This is me. Okay. Yeah. Take into account that black fabric to avoid light coming into the detectors, because the detectors has also the photovoltaic effect. Okay, so it's very important to take out the ambient light from the experiment. And in principle, the problem here is that the fluence you have is limited. There you have any fluence you want, any flux you want, and you can, in an hour or two, you got up to 1 to the 16 neutron equivalent 1 MeV by square centimeter, huge. Here, in an spallation facility, the typical, we have one there at CERN, and also another one in Los Alamos. In Los Alamos laboratory, Lance is the name of the facility. Those are the only two facilities for neutron, very fast neutron. Here, at the end of, we have neutron up to 1 GeV. Okay, but the flux is limited to 10 to the 70. Sorry, 10 to the 7. So it's not a huge flux, so you need a lot of time, and that is the reason those experiments are made in the dump, without interfering the main experiments in the chamber next to in the other room. Okay, so in principle we can make experiments in this thing. There will be a huge it's a project now starting to be built in Granada, Escúzar, where we will build a deuteron beam accelerator to test materials under huge fusion equivalent neutrons, 14 MeV. Probably it will be working or giving results in 2032, 2033. So this is very important for materials in terms of fusion reaction and this kind of energetic things. Fusions could be not important in this planet, but sure, fusion engines will be extremely important to the exploration of the solar system. But up to now, we have no materials to withstand a the huge amount of neutrons, 14 MeV, coming from deuterium, tritium nuclear fusion reactions. So, one question?
I just wonder, this spallation facility at CERN is the same as ISIS in Oxford, with proton into
Yes,
tungstenium
Yes.
target and
Yes.
then produces.
yes, yes. But the facility in Oxford has a more restricted access because they were interested in muon physics. So sure, they have an spallation. Even probably in Sweden we will have the European spallation source. But for the neutron physics groups, we are a disturbance, basically. When we go with our devices to know if our devices works in their environment, basically they say, go there, but make no noise, etc., etc. That is the reason we decided in the community to make our accelerator in Granada. So we don't want to be remembered as a nuisance in very important physics experiments. So we will make our engineering experiment using neutrons. That's only a joke. Okay? So we will go into electronics again, into signal electronics. TID is important, displacement damage is important, but those are aging effects, okay? But there is another thing, it's a very huge nuisance, that are transient ionization, single event currents. The currents generated in the device because of instant ionization coming from a high energy particle, okay? In particular, this is the detection of the particle, but it is an unintended detection. We don't want to detect things with your electronics. We want electronics working properly, generating signals and registering memories and whatever, but not to be disturbed by transients. The name in the trade is glitch. You can have glitches coming from electricity in the typical behavior of the device, but also you can have these kind of things. So we have to fight against ionization glitches. In the old days, not so old, we were happy with the 32 nanometers scale. That's old, okay? Nowadays, we are using every day, not even MOS transistor, we are using FinFET transistor, another thing that we'll discuss probably on Sexta-feira. And in those years, 60 nanometers was the maximum miniaturization possible. Wow, 60 nanometers. Today, this is huge. Okay? In the field of analog electronics, analog microelectronic design, we wanted to stop at 28 nanometers because 28 nanometers is the frontier between MOS transistors and FinFET transistor. Nowadays, we are starting to get into the market the next generation gate-all-around devices. Gate-all-around devices are around 2 nanometers. And probably the Moore laws will stop at 0.5, 0.2 nanometers. Okay? This has an impact in the foundries you find. For example, Intel is almost bankrupt because it's true. It's almost bankrupt because it cannot follow beyond 2 nanometers. And for that reason, President Trump decided that TSMC will bought 50% of Intel. The only foundry capable of going beyond the 2 nanometer scale is Taiwan Semiconductors. So if I'm on air. So if for some reason Taiwan is invaded by who knows who, okay, prepare to close the war because your devices will be not functioning anymore. That's the situation today. Back to ionization. Today, this is 65 nanometers. Today, almost every transistor could be affected by ionization particles. In particular, the proton flux we found in any geostationary orbit. Geostationary orbit is critical, for example, to establish connections, digital direct television, from Europe to Brazil. If for some reason someone cuts the cables undersea. That's our very last wall of communication. So proton flux is important there. Doing our homework for the TSMC 65 nanometers, the foundry we choose for RD53, the vulnerabilities start at 5 MeV by square centimeter and milligrams. This means that any alpha particle emitter is capable of generating single event effects in 65 nanometers. Remember, 65 nanometers is old technology. Nowadays, analog design is in 28 nanometers, and digital design is going the 2 nanometers path. So this was presented at Mixan 2016. Below 65 nanometers, single event effects will be common. So the thing is not to avoid single event effects, because we cannot. The thing is to have the things properly working in the spite of the presence of single events. Dime. It's over? Oh, okay, it's over. Sorry. The next session, I will go into electronics. Wow. Okay, thank you. See you on Wednesday.
Any questions?
Any question from online audience? No question at all? Any question from here? You're exhausted. Me too. Okay, thank you.